Good morning. Welcome to the lecture on design of RCC elements. Today we are going to see about the limit state of collapse in flexure. So far we have seen the working stress method, how to take care of your stress strain blocks in working stress method, and how to analyze your beams and design your singly and doubly reinforced beams in working stress method. Then we have seen about the limit state design of slabs also, that is one-way and two-way slabs. In this lecture, today we are going to see about the stress strain block, then your design stress block parameters in limit state design of collapse under flexure. Okay, let me get through it. First one, the assumptions involved in your limit state of collapse for your flexure. The first assumption in our mind is the plane section will remain plane even after bending. Suppose for example this is your plane section. After getting your loads, even after bending also it should remain plane after getting your loads. Then the maximum strain in a concrete at the outermost compression fiber should be 0.0035. That is your ultimate strain in the concrete allowed is about 0.0035 in bending. Then here we are neglecting the tensile strength of your concrete, that is the main assumption over here. Then the compression stress distribution in concrete and strain in concrete may be in the form of rectangular fashion, that is the distribution part is in the form of rectangular fashion, trapezoidal fashion and parabolic fashion. Then the maximum strain in the tension reinforcement is Fy divided by 1.15 ES plus 0.02. After this only your strain should get failed. Before that it should not get. After reaching this strain value, your steel part should fail. Okay. These are some of the assumptions for the elements to be designed under flexure. Let me clarify what is meant by flexure. What are the elements will be subjected to flexure? For example, everyone knows that when a flexure comes to the mind, only beam as an element will capture the flexure. It is not so. An element having its horizontal axis in one direction and capturing your load in opposite direction, that is your perpendicular direction, will be subjected to bending, right? This bending is nothing but flexure. This is not only for beams, it can be applicable for many elements. I will discuss that. Say for example, beam is a horizontal element, so you are getting your loads perpendicular to your axis of your member. At the same time, the slab, that is also a horizontal member, you are getting your load in perpendicular direction of your axis of your member. So the slabs also will be subjected to flexure. Then sometimes the shell elements also getting their load in perpendicular to the axis of the member. It also we can call it as a flexural member. In some cases, this is a column, this is a vertical member. Usually the column we are considering it as compression member. When the column is capturing your load in lateral direction, suppose for example lateral forces, that is wind force or earthquake force is a major criteria in your column. This is your axis, you are getting load in this direction, it will be subjected to flexure. So we don't call beam alone as a flexural member, we can call the vertical elements also. Other vertical elements such as the retaining wall. The retaining wall we are mainly constructed to retain a soil or to retain a mass on other side of your structure. This retaining wall is capturing your load in lateral direction, having its axis in opposite direction, so that it also will be subjected to flexure. In some cases, the ordinary concrete wall may also be subjected to flexure. Most of the cases, when the element is capturing the flexural behavior, it will be associated with some shear. That shear is nothing but transverse shear. When you are going for a flexural member, when you are analyzing a flexural member, you need to check for shear also, whether this flexural member will fails in shear or not. Shear is nothing but it is like a brittle failure in your structure. It is like a holding your scissors and passing your scissors into the sheet of the paper, you are cutting through. This is like a breaking through in your structure. So you need to check shear also for each flexural members. Okay, let me begin with the stress block parameters for flexural members. Okay, I have drawn a beam of breadth B. Then this is the total depth D. When it is having the reinforcement, I can say this is my effective depth. Okay, then this is the ultimate strain. In our assumption itself, the maximum strain in concrete at the outermost compression fiber will be 0.0035. Then this is the proof strain, that is 0.002. This is the concrete strain in concrete, that is 0.002. This is the ultimate strain, epsilon Cu. Then at the level of steel, we are drawing strain in steel. It should be greater than or equal to 0.87 Fy by Es into 0.002. So the strain in steel should reach, when this value you will get this value. It should reach, this ultimate should be greater than or equal to this value. After this value, your strain in the steel should get fails. Okay, let me draw a stress block. This is the outermost compression fiber. You will be getting a value in straight line, that is 0.456 FCK. This 0.45 FCK where we got is when we draw a stress strain block for concrete, will be having this value. This value is nothing but FCK. This is your characteristic compressive strength. This you are being taken for cube. This characteristic compression strength you are taking for cube. When you have to take the characteristic strength of your structure, this line is nothing but idealized curve, that is FCK for structure. For structure, you will get the value of FCK divided by 1.5, that is the partial safety factor for concrete, so you will get 0.67 FVK. For design purpose, you need to draw a design curve. This is the design curve. This design curve, you will get 0.67 FCK divided by 1.5, so you will get 0.45 FCK. This is the stress in concrete, so the ultimate stress will be 0.45 FCK. That is, for a structure, it should be 0.67 times the compressive strength of your cube. You can write structure FCK should be 1.67 times the FCK of cube strength. Okay, so you will get the ultimate stress in your concrete as exactly I have written it as 0.446 FCK, that is 0.45 FCK. Then the compression is 0.36 FCK B into XU. This compression will take place at the line of your concrete strain, that is epsilon C. At 0.002, you have a straight line variation. That straight line variation, the force occurring at the center is nothing but Cu. The depth of center of compression force taking care in your stress block is 0.416 XU. After that, your variation will be in parabolic fashion. So, your stress block will be somewhat rectangular here, then again it starts your parabolic fashion. Okay, the stress in steel Tu is nothing but, this is 0.87 times Fy divided by A. How you are reaching the 0.87 times Fy is nothing but, when you draw stress strain curve of your steel value, this is in the linear form, then again this will be in Fy, this is your yield stress in your steel. Then For design stress, you will get Fy divided by 1.15. 1.15 is nothing but partial safety factor for your steel. So, you will get 0.87 Fy. This is the design stress in your steel. So, 0.87 Fy into the area of steel what you are been providing. This is AST. So, we know that from the stress block and the strain block, the maximum stress in the concrete is 0.45 FCK. Then maximum strain is 0.0035. Maximum stress in steel is nothing but 0.87 Fy. Now, we can get the area of stress block Cu is equal to 0.36 FCK B into XU. This is 0.4, this is your breadth, this is your depth. So, you will be getting 0.36 FCK B into XU. Okay. At failure, what will be your strain in your steel? At failure, the strain in your reinforcement provided should not be less than this value. It should be greater than this value. Beyond this value only, you need to get your ultimate strain in your steel. That is the main thing in the main assumptions we have in your limit state method of flexure. Okay. You know that XU is equal to K into D. This K is nothing but epsilon Cu. This is your strain in concrete divided by epsilon Cu concrete plus epsilon Su. When we consider Es is equal to 2 into 10 power 5 Newton per mm square, for this we can write maximum Xu max divided by D as, this is, we all know that epsilon Cu is your ultimate concrete compression 0.0035 divided by, you can put this value 0.0035 plus 0.87 by Es into 0.002. After substituting this value, you will get 0.005 plus 0.87 Fy divided by Es. Okay. Okay. Now we will get the value of Xu max by D is equal to 700 divided by 1100 plus 0.87 Fy. We have Xu max by D variation for variation in your yield stress of your steel. When you are providing 250, the limiting value of Xu max by D is, for 250 it is 0.53. When you are providing 415 steel, it is 0.48. When you are providing 500, this is 0.46. Okay. These are some of the values. It is there in codebook IS 456 page number 20. It is there. When your problem is given for your 415 value, you can directly take it as Xu max by D is 0.48 and you can calculate the depth of your neutral axis in the easiest manner, whereas this is what critical in working stress method. Okay. Now we are going to see about modes of failure. I am drawing a beam of breadth B. This is my depth D. I am drawing the neutral axis. I am drawing for my balanced section. The strain. This is Xu max. When I say Xu max, the section will be under balanced section. This is the balanced section neutral axis. Then this is epsilon Cu. This epsilon S is equal to epsilon Sy. Epsilon C is equal to epsilon Cu. When steel and concrete both are simultaneously yielding, you will get epsilon Cu and epsilon Cy. At the time you will get Xu max value. Then this is the beam. Your actual neutral axis is here, but when you are getting neutral axis here, this is epsilon Sy. This total strain in steel will be epsilon S, which is greater than epsilon Sy. Here this is epsilon Cu. This is the actual neutral axis you are getting for the section. This is balanced neutral axis. So you can call this section as when epsilon Sy, epsilon S is greater than epsilon Sy, you can call it as under reinforced section, or else when the section is like this, same beam, this is your balanced DNA, balanced neutral axis. When you are getting actual neutral axis over here, this is epsilon Cu. This value is, the total is epsilon Sy. What you are getting is epsilon S, where epsilon S is less than epsilon Sy. This is nothing but over reinforced section. This is under reinforced section. This is over reinforced section. Why we are calling this as modes of failure? When a section will get fail, when epsilon S is equal to epsilon Sy, then epsilon C is equal to epsilon Cu, the section will get fail. At the time we can directly calculate the depth of neutral axis as Xu max. This failure will happen simultaneously over for concrete and steel. That's why we are calling it as balanced section. Okay, clear? Then this section, why we are calling it as under reinforced section is that because in the name itself under reinforced, steel is in less amount, so the concrete will get yielding. So yielding in later times. So the steel is getting yielded. Your steel is epsilon S, whereas epsilon S is greater than your epsilon ultimate. Your ultimate is over here, but it is training more than your ultimate. That's why it is under reinforced section. So this section is mainly governed by your steel part. Steel is yielded first. That's why we are calling it as under reinforced section. First failure is considered in steel material. Okay. Why we are calling it as over reinforced section is that the reinforcement is too large in this beam. So the concrete will get yield first. Your steel will be epsilon S. This is your ultimate, but this is epsilon S. So epsilon S will be less than your epsilon Y, where we have more amount of concrete yielding part. That's why we are calling it as under over reinforced section. In over reinforced section, the concrete will be governing criteria. Okay, let me have some clarification based on this diagrams. First one, Xu by D is equal to Xu max by D. You can call it as balanced. Second one, Xu by D is less than Xu max by D. You can call it as under reinforced. Third one, Xu by D, which is greater than Xu max by D, you can call this as over reinforced. Or else we have equal to failure strain, more than the failure strain, less than the failure strain. In all the ways we can explain this. Okay. Now we are going to see about the limiting percentage of reinforcement and limiting moment of resistance value. Okay. Now failures based on percentage of steel provided in tension zone. we have seen three types of failures: balanced, over reinforced and under reinforced. These failures are mainly based on your percentage of, when your percentage of steel is less, you can call it as under reinforced. It is more, we can call it as over reinforced. Okay, how to calculate XU max by D from this percentage of reinforcement? We know that the formula 0.36 FCK B into XU, TU is equal to 0.87 Fy into AST. Now from this value you can write XU by D is equal to 0.87 Fy AST divided by, this is what the XU, 0.36 FCK B into D. Here you are adding D, here also you are adding D. So you can simplify this value as 2.417 Fy by FCK into AST by BD. This AST by BD you can write it as PT, that is PT is equal to 100 AST divided by BD, that is your percentage of reinforcement. So when you want to get the limiting percentage of reinforcement, you can directly put XU max by D is equal to 2.147 Fy by FCK into your percentage of reinforcement. So this is the limiting XU max by D value. Then limiting moment of resistance. The limiting moment of resistance, we know that this is the Cu, this is Tu, this distance is nothing but the lever arm Z. Z is equal to, this is 0.416 XU max. Z is equal to the total depth, this is small d, this is your effective depth, minus 0.416 XU max. So you can directly calculate the limiting moment of resistance. Lever arm is equal to small d minus 0.16 XU max. Mu limit is equal to 0.36 FCK B XU max into, this is the formula of compression force, force into the distance travel. So D minus 0.416 XU max. Now you will get the value as 0.36 FCK into XU max by D into 1 minus 0.416 XU max by D into BD square. Here we can take this as moment resisting coefficient. So when you change the value of Fy, for example you are putting steel as Fe250, the Mu limit will be, this value will be, this XU max is purely based on your Fe250, that is your yield stress in your steel level. So when you change this value, your main content will be changing. It is there in your code book. Rightly said, when you give a 250, you can directly plot the values for XU max by D. When it is 250, you will get the value as 0.148 FCK BD square. For Fe 4 and 5, the Mu limit will be 0.138 FCK BD square. For Fe 500, Mu limit will be 0.133 FCK BD square. These are some of the limiting values we need to calculate to check whether our section is under reinforced or over reinforced. After arriving these formulas, we can directly get through it, or if you know XU max by D value for subsequent yield stress in your strain, you can directly check the value of 0.148. If it is 4 and 5, 138, we can directly substitute and we can directly check our moment of your section whether this is less than mu limit or greater than mu limit. When it is greater than, why we need this formula? When mu is greater than mu limit, mu is less than mu limit. You are checking the failure condition, whether it is been undergone by under reinforced section or else by the over reinforced section. These are some of the criteria you need to follow for your design of your sections. Now we are going to see only one problem related to singly reinforced section of flexural beam. Okay. Problem 1. RC beam of size 300 by 700 mm having cover of 40 mm to center of reinforcement. Design a beam if it is subjected to total bending moment of 150 kilonewton meter. Adopt M20 and Fe 415. Okay, this was the problem given. Let me draw the problem. This is 300 mm. This is 700 mm. They have given cover of 40 mm to the center of the reinforcement. From the center, this cover is 40 mm. So you can directly calculate D as 660 mm. Okay. First thing, they have given you the moment value, that is your bending moment value. You need mu is equal to, the ultimate load should be multiplied by your factor of safety into 150. So you will get 225 kilonewton meter. Okay, this was the first step. Then second step, now we are you need to design a beam subjected to this. Design a beam in the sense the size is given, you need to arrive your reinforcement for this section. For that, first you need to analyze where is your XU max value. Okay, now XU max by D is equal to, the problem is Fe 4 and 5. So the XU max by D value, you can directly take it from your code book of page number 70, 0.48. From this value, you can check your mu limit. Mu limit is equal to 0.36 FCK, that is 20 into 0.48 FCK into XU max by D, this value 1 minus 0.416 into XU max by D value into B into D square. So after substituting 300 into 660 square, this is 300, this value is 660. Now you will get some value around 360.8 in 10 power 6 Newton mm, or else 360.8 kilonewton meter. The given value mu is less than mu limit. So you can call rightly this section as under reinforced section. If you know that this section is under reinforced from your XU max by D and mu limit, mu the given is 225, which is less than your mu limit, you can proceed this under reinforced section which is being governed by your steel part. Now you can write mu is equal to 0.87 Fy AST D into 1 minus Fy AST divided by FCK into BD. This is the failure criteria under reinforced section. So the steel is the governing part here. The steel will reaches its yield point at first, after then the concrete is been reaching. That is the main theme of this area. So we are been deriving for under reinforced section over your steel formula. So if you substitute mu, that is 225 into 10 power 6, that is equal to 0.87415 into AST into 660 into 1 minus 415 AST divided by 20 into 300 into 660. Okay, you will get AST as 1062.5 mm square. This is the design. Design is somewhat, if the section is not given, you need to arrive a section and calculate your AST. Then whatever the calculated AST, you need to provide it in your section. Before that, you need to check whether it is under reinforced or over reinforced section. Okay, in tomorrow's session, we are going to see about that doubly reinforced section, the stress block parameters and with the problem. Okay, let me conclude this lecture today. We have seen so far about the limit state design of flexure. What we have seen about what is meant by flexure, what are all the members will be subjected to flexure, in what way it will be subjected to bending when it is capturing its force in what axis. We have seen those things. Then we have seen how to draw the stress block parameters and strain block parameters under limit state method when the concrete will reach its maximum compressive strain and maximum compressive stress over there. Then we have derived a problem. Then based on your mu limit value, you need to calculate from your code book. Based on your mu limit, we have seen the failure parts of your section, that is the modes of failure of your section, whether it is balanced section, under reinforced or over reinforced. Then we have touched only one problem related to singly reinforced section, how to design those beam in a simple way. Okay, next lecture we will see about the doubly reinforced section, stress block parameters and a problem. Thank you.